Hello everybody, so I will start my today's coding practice. So today's question is this: flip equivalent binary trees. Okay, so in this question, I will be given a binary tree T, and the flip operation is defined as choose any node and swap the left and right child subtree. Yeah. And binary tree X is flip equivalent to a binary tree Y if and only if we can make X equal to Y after some number of flip operations. Given the root of two binary trees, root 1 and root 2, return true if two trees are flip equivalent or false otherwise. Okay, so let me firstly clarify the understanding of I mean, for this question. So, firstly, I were given the two trees, like this and this, and I will try to see if I can do the operation, flip operation, any number of times and make sure that these two trees become equivalent. I mean, the same. And if they're the same, I mean, if I can make them the same, I can say this tree is these two trees are flip equivalent, otherwise no, and return false. I see. Okay, good. So let me, yeah. Okay. And just to clarify, the given tree X or Y can be null because the number of nodes will be 0 to 100. And also, oh, the condition says each tree will have unique node value in the range 0 to 99. So I see. It says the same number doesn't appear. Okay, so I think let me show one more example and let me start the implementation. So I actually have a kind of image of implementation approach already. I have already in my mind. So when I take a look at node 1 and 1, yeah, they're the same. 1 and 1 are the same. So I will take a look at the child trees. And because 1 is 2, 1 is 3, and I can say 2, 3 pair is the same, but the order doesn't order isn't the same. So I will compare 2 subtree with 2 subtree in the left. And I will compare 3 subtree with 3 subtree in the right. So then I will compare 2 subtree. Yeah. And when I compare 2 subtree, I can say, so node are the same. So yes, and it already confirmed. And I will take a look at the child nodes, which are 4 and 5, and 5 and 4. They're the same. So I can continue. And because if I find this, like 5, 3, I can no longer continue because 3 sub 3 can never equivalent with any of 2, 4 sub 3 or 5 sub 3 in the left. So yeah, in this case, if I swap this 3, 2, I can make them. It is possible that I can make them equivalent. So and I will do it recursively. So the main idea I have in my mind is I will use the recursion and I will take a look at node root files first. I will first check root, then check left right pair, then recursively check. Yeah. So yeah, I think this is the way I can take. And fortunately, it's said node values are unique. So it never be like 1, 2, 2 sub 3 and 1, 2, 2 sub 3. If they're the same, I can say I have no idea which, in this case, I have no idea if, yeah, in this case, I have no idea if the rest of the tree is like this or rest of the tree is like this, which means that I have to compare each case of, you know, so in the line 13 logic, I have to compare, I mean, okay, let me say 2A to B to C to D. In this case, because two are the same, I have to think of two cases. Case one, I check 2A is equivalent to D and 2B equivalent to 2C. Also, I have to check the case when 2A equivalent to C and 2B equivalent to 2D. I have to check these two conditions, two cases, and if either is true, I can say there's the equivalent as a whole tree. But I don't have to do this in this question. Okay, so that being said, I will start the implementation. I actually need this. So I can say, but still I have to firstly check if they know or not. So if, yeah, this is the kind of base condition I have to take care. So if both of them are known, they're the same, so I will return true. And if only one of them is known, I will compare known and some tree, so I will return false. And after that, it is confirmed that root 1 and root 2 are not known, so I can safely use dot value. Okay, then if two values are the same, I will compare left and right. And what I should do is, okay, so left one, right one is, I think I can use it in this way. So, I'm not 100% sure I can use this, but what I want to do is like this. So if these are not the same, I will return false immediately. I have to take care that root one dot ref can be node, I mean null. So in that case, I'm not 100% sure this works, but basically what I like to do is if the set of node root values are, oh no, I think that it doesn't work. Let me, so I will do it more, Okay, so okay, so I get these numbers in this way, and then I will do something like so. mm, 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 mm. I will check this. And in another case I have to take care is like this. Okay, so in this case, I will compare in line 44, I will compare left 1 and right 2. Also, I will check right 1 and left 2. And 3. Otherwise, I will return false. So when I do this, it is guaranteed that this recursive function, flip equivalent, is called with root 1 dot value is equal to root 2 dot value. Yeah. From the second recursive function call. However, for the first call, root 1, root 2 dot values cannot be they're not always equal, so I have to still include this check in line 34. Okay, let me quickly check this my code. So I will simply check with this example and this example. Okay, in this case, in line 30, in the first recursive function call, root 1 is not known, root 2 is not known. So I will go to line 43. And if they are not equal, so I don't return, sorry, root 1 dot value, root 2 value are equals, which are 1. So I don't return, and I go to, I write 46. And here, what I will get is, oh, wait a minute, so root 1 is none. Oh, no, this is completely wrong. Yeah. So here, in the left one of root 1 is, I mean, tree 1 is 2, because root 1 that left is node 2, which is not known, and never gets the value 2. But right 2, this should be known, because root 1 dot right is known. Then I will take a look at the left 2, which should be known, because root dot 2 dot left is known. And right 2, this should be 2, because root 2 dot right is node 2. So I will take a look at the value. So it should be 2. So in this case, comparing L1, L2, R1, R2, so line 51 is not met. So I will go to line 53, and this condition is met. L1, R2 are 2, L1, L2 are R1, L1 are none. Okay, so then I will return root 1 dot left, root 2 dot right comparison. So I will compare node 2 and node 2. And also I will compare node known and node known. And for the first half, node 2 and node 2, I'm pretty sure it will be, all of the grandchild are known. So it finally returns, yeah, true. And for line 54 latter half, this is known and known. So it goes to line in the recursive code in line 38. Both of them are known, so it will return true. So line 54 in the end returns true. Okay, good. So I'm pretty sure of this code. I have some lines which I haven't went through, which is line 52. So let me quickly check this. L1, L2. Yeah, I'm pretty sure this is correct. And also I didn't cover line 56. This is obviously correct. Okay, so I'm pretty confident on my code, so I will run it. Good. And then submit it. Great. Okay. So I will quickly do the, complexity analysis. So assuming that the number of nodes of root 1 is n1, number of nodes in the second tree is n2, time complexity should be mean of n1 and n2, because I don't have to, so at max, I have to check all the trees. But since that there is the completely same tree and node 2 has some more. In that case, in the worst case, I will check all the nodes which are included in N1, which is a smaller tree, but I don't have to see any more in N2 because having some more nodes means that they're not equivalent anymore. So I can stop the comparison at that time. So in that sense, the time complexity would be meaning of N1 and N2. And for space complexity, I just need the space for, you know, um, the recursion stuff. So it should be the height of the tree, exactly. And because this is a binary tree at max, the height can be, up to N1, N2. Yeah, height of tree one, height of the tree could be at max number of the nodes in the tree. Yeah, think of the linked list case. So if there are n nodes and the tree is like the linked list, the height would be exactly the number of nodes. So that's the worst case. Okay. Okay, good. Okay, so I will quickly wrap up and finish my today's coding practice. So in today's question, flip equivalent binary trees, I did a recursion to compare two trees. And thanks to the conditions that the unique node values in the tree are unique, the recursion is a bit simpler. I just have to compare the subtree, which can be equivalent, yeah, recursively. Okay, so that's it. Okay, thank you. I start finish my today's coding practice with this. Thank you so much. Bye.